What if I told you there's a material that sounds like it was pulled straight out of a sci-fi movie? Something that can literally pull fresh water out of thin desert air, vacuum carbon dioxide right out of the atmosphere, and even deliver medicine precisely to cancer cells, leaving healthy cells untouched? Well, it's not science fiction. It's real. And today, we're going to dive into the story of metal organic frameworks.
All right, so what's the secret sauce? What gives this stuff its superpowers? Believe it or not, it's almost entirely empty space. I know. That sounds like a total contradiction. How can something that's mostly nothing be so revolutionary? Well, as you're about to see, that emptiness is exactly what makes it so powerful.
To really wrap your head around what mostly empty means, we have to talk about surface area. Take a look at this number, 10,000 square meters. Now, on its own, that's just a big number, right? But it is the absolute key to understanding how unbelievably porous these materials are. Let me put it in a way that'll really blow your mind. Okay, let's dive into this because this is where it gets wild. Imagine you have a tiny piece of a moth, about the size of one sugar cube. Now, if you could magically unfold all of its internal nooks and crannies, all those surfaces inside, you would cover an entire football field. Yeah. How is that even possible? Well, the best way to picture them is to think of them as microscopic sponges. But, and this is the crucial part, unlike the random chaotic holes in a kitchen sponge, a moth has a perfectly organized crystalline structure. Think of it as having millions of tiny identical parking spaces that are custom designed to catch and hold very specific molecules. Right, so the big question is, how on earth do you build something so incredibly complex and so full of empty space all at the same time? Turns out, you build it with something that's a whole lot like molecular Legos.
Okay, here's the official textbook definition. I know, it sounds a little dense. Metal ions, organic molecules. But don't worry, the actual concept is beautifully simple. It really just breaks down into two main building blocks.
Remember those molecular Legos? Here they are. First, you've got your metal ions, or nodes. Just think of these as the little connector joints, the hubs, kind of like tiny magnets. Then you have your organic linkers. These are the Lego bricks themselves, the struts that snap between those magnetic hubs. And here's the magic. By picking different metals and different linkers, scientists can custom build a nearly infinite number of different frameworks. I love this quote because it just nails the breakthrough. Before the pioneers in this field did their thing, and by the way, this work is so groundbreaking, everyone's just waiting for the Nobel Prize to be announced. Creating new materials was often a shot in the dark. You'd throw some stuff in a beaker and hope for the best. It was gambling. But these guys, they wrote the instruction manual. They gave us the blueprints to design and build molecules with purpose. And that ability to build with purpose, to be a molecular architect, is why moths aren't just some cool lab experiment. Nope, they are being engineered to go after some of the biggest problems humanity is facing, from cleaning up our planet to revolutionizing medicine. First up, the big one, climate change. With moths, you could design a filter where the pores are the exact size and shape needed to snatch CO2 molecules right out of the air, say from a factory smokestack. It's like having a hyper-specific vacuum cleaner built just for greenhouse gases. So just how much better is this new method? Well, let's put it side by side with the old way. The traditional method, amine scrubbing, is kind of like using a messy chemical mop. And it's an energy hog. You have to use a ton of heat to wring out the CO2 it captures. But the MOF method is so much more elegant. It grabs the CO2, and then all it takes is a little low-pressure steam to release it. We are talking a massive energy savings, which makes the whole idea of carbon capture way more practical. Okay, this next one is just incredible. What if you could have a well that pulls fresh, clean water directly from the air, even in the driest place on Earth? Well, that's not science fiction anymore. Scientists took a device based on MOFs and tested it in Death Valley, one of the hottest, most arid places you can possibly imagine. And the results were just stunning. For every single kilogram of this moth material, they were able to pull 285 grams. That's about a full cup of pure water right out of the desert air every day. And the best part? The whole system is completely passive. At night, the moth sponge just soaks up the sparse water molecules from the air. Then, during the day, the heat from the sun bakes that water out, clean and ready to drink. It uses zero energy except for sunlight. So we've talked about saving the planet, now let's talk about saving lives. MOFs can be used as tiny, precision-guided delivery vehicles for medicine. Think about chemotherapy. The problem has always been that it's like a sledgehammer. It kills cancer, but it damages healthy cells too. Now, imagine putting that powerful medicine inside a microscopic cage that has an address label on it, telling it to only go to a tumor. So here's why this is such a game changer. These tiny cages can carry a huge amount of a drug, almost a quarter of their own weight. But the truly brilliant part is the release mechanism. They're engineered to pop open and release their cargo only in the slightly acidic environment around a tumor. That means the medicine hits the cancer hard and leaves the healthy tissue alone. You can just imagine what that means for reducing those awful side effects.
Now, this all sounds almost too good to be true, right? So what's the catch? Well, like any revolutionary technology, MOFs aren't perfect, at least not yet. There are still some pretty big hurdles to clear, but we have a secret weapon that's letting us leap over those hurdles faster than ever before: artificial intelligence.
So here's what scientists are wrestling with. Some of these MOFs are a bit delicate. They can fall apart in humid air, which is a problem. They're also expensive to produce right now, and, it's one thing to make a few grams in a lab, it's a whole other challenge to make industrial-sized tons of the stuff. We basically need to find the Goldilocks MOF for each job, one that's tough, cheap to make, and lasts a long time.
And finding that perfect, just right MOF is like looking for a needle in a haystack the size of a continent. There are literally millions and millions of possible combinations of metals and linkers. Trying to test them all by hand in a lab would take centuries. This is where AI comes in and just changes the game completely. It's like a super fast, super smart matchmaker for atoms. The process is just brilliant. First, the AI just imagines millions of possible MOFs in a simulation and predicts what their properties would be, no lab work needed. Then it puts all those virtual candidates through a digital boot camp, screening for the ones that would be best at a specific job, like carbon capture. And finally, it spits out the perfect recipe for a scientist to go into the lab and synthesize the absolute best one. This is cutting down research time from years, even decades, to just a matter of months.
So when you take this incredible new material and you pair it with the insane accelerating power of AI, where does all this lead? Well, it leads us right to the brink of what many are starting to call the MOF decade. Think about it. Think about how completely smartphones transformed our world in the 2010s. They changed everything about how we communicate, work, and live. That is the exact scale of transformation that experts are predicting for MOFs in the 2030s, as they finally move out of the lab and into the world all around us. So what does that future actually look like? We're talking about power plants with smokestacks that literally clean the air instead of polluting it. We're talking about personalized medicine designed specifically for your body and your illness, hydrogen-powered cars that can be refueled in 5 minutes, even smart buildings that are self-sufficient, harvesting their own water and purifying their own air. So there you have it, the wonder material that's mostly empty space, built with molecular Legos, and accelerated by AI, is ready to solve our biggest problems. At this point, it's no longer a question of if metal organic frameworks will change our world. The only real question left is just how quickly and how completely are they going to do it?